Hello there, my name is Gaurav Shukla and I'm here to give you a very brief explanation of my project image denoising, particularly image denoising using convolutional autoencoder. So let's get to the very basics first. What exactly is image denoising? So basically image denoising is removing any kind of noise that is present in images due to any number of factors, mainly being environmental, but sometimes it is also due to the sensors or due to the methodology used in capturing the images, or maybe the lens. It is really essential for improving video quality and downstream performance. And then let's get to the next bit, that why is it so important? Why is image denoising so important? So it is important because it basically enhances the quality in so many of the operations like medical imaging, satellite data, surveillance or security systems, etc. It is also a very important pre-processing step for many of the significant image operations and methodologies used out there. For example, object character recognition, object detection, compression, etc. Now, the last bit, the convolutional part or the convolutional autoencoder part, what exactly is? So convolutional autoencoder are basically neural network architectures that are designed to learn compressed representations, and they are also particularly effective for image representation or reconstruction tasks. Now that the introductions are out of our way, then let's get to the motivation, that why this problem, why did I choose this problem, and why did I choose to solve it in this way. So let's start again, that what are its real world significances, relevance, and why did I choose this problem. It is because most of the imaging systems out there introduce noise like a second nature to them, because of the sensors they use, or the transmission technology, or even the compression techniques they use to store all these images. And accurate denoising can be very critical for diagnostic and recognition systems. Then like we all know that there are many filters and simple image operations that can be used to remove or at least decrease the amount of noise that are present in the images. Then why do we need to use such a heavy duty system, or even in fact a deep learning system? Why do we need to use such large systems when the same kind of work can be done using simple filters? Well, that is because all these filters, Gaussian, median, mean, max, etc., they basically blur the images, and therefore decreasing the amount of details that can harm the oncoming operation, for example object recognition, segmentation, etc. Also, most of these filters work in the frequency domain, which doesn't really consider the spatial adaptability of noise. Then why did I choose to use deep learning, particularly convolutional autoencoder? It was because it learns noise patterns directly from the source, directly from the image data, and it captures both the global and local structures, and it works in the spatial domain. Also, it automatically optimizes for perceptual and statistical fidelity. So let's get to the methodology, particularly the model design and workflow, how it works. So starting with the dataset and the pre-processing tasks, the dataset I used is pretty simple and basic. I used the handwritten digits dataset, the MNIST dataset, which is basically a collection of handwritten digits in the form of 28 by 28 grayscale digit images. And then as pre-processing, I normalized all these images that were ranging from 0 to 55, down to a range of 0 to 1, 0 being the darker regions and 1 being the brighter regions, that is the digit structure. I also added a synthetic Gaussian noise to artificially model the noise present in real world captured images. Then, getting to the convolutional autoencoder architecture, the encoder part was as follows. It started with a convolution layer consisting of 32 filters, then a max pooling layer, followed by another convolution layer consisting of 64 filters, followed by a max pooling layer. This encoder part basically compresses the image to a lower dimensional feature map, basically encoding the image. And then the decoder part of the architecture. The decoder part of the architecture was as follows. It started with a convolution layer of 64 filters, followed by an upsampling layer, then another convolution layer of 32 filters, another upsampling layer, and at the end of it all, a convolution layer with a sigmoid activation function. The decoder basically reconstructs the image from the encoding provided by the encoder. Then the training setup for this project. For the training, I considered the binary cross entropy loss function and tried to minimize it. I also used Adam optimizer for the training. There were also additional metrics that I calculated, for example, peak signal to noise ratio or structural similarity index, which we'll talk about later in detail. I also added some early stopping and model checkpoints, particularly to check for target loss rate. If the target loss was reached, then there would be early stops, and if the current loss exceeded a particular predefined limit, then I would stop the training and start the training all over again. Let's get to the results in conclusion, particularly what we achieved during and after this project. What we achieved can be classified into two categories: the quantitative uh, performance and the qualitative insights. For the quantitative performance, we have the peak signal to noise ratio and the structural similarity index, with the peak signal to noise ratio being around 27 to 28 decibels, which is not very great but decent. And then there was the structural similarity ratio or index, in which we basically check how much were we able to reconstruct the image, which we achieved around 90%, which is pretty great. Not really best, considering that we were using a heavy duty model and deep learning, but still good, better than the filters, Gaussian filters and median filters. Then what were the qualitative insights? There was particularly low reconstruction loss, barely around 9 to 10%. Then the model preserves digit contours pretty well. The digits are really recognizable, at least to the human eye. I have yet to feed them into another model for classification, which could be a pretty useful future scope for this project. Then our model was also very robust to moderate Gaussian noise. I didn't try to overdo with the Gaussian noise, because it would really defeat the purpose. The Gaussian noise was around 30 to 40% of the image, which is still pretty good, I think. Also, our model was really good at visual comparisons that show strong fidelity. Like the reconstructed images were really close to the original images. So, in conclusion, we can say that convolutional autoencoders are effective for grayscale image denoising and lightweight, fast, and generalizable models. Lastly, we come to the future scope of this project, particularly what can be improved and what are the applications for this kind of project. So the model enhancements that can be done are we can use deeper encoder and decoder architectures, like adding resonant blocks, etc. And we can also use skip connections, like the type we use in unit style architectures, or we can also incorporate or try to incorporate attention mechanisms to give more attention to the parts of the images that have been continuously ignored. Other than that, we can also expand our datasets, like using larger and high resolution image datasets, for example BSD 500 or DIV 2K. We can also try to train our data on real world noisy images gathered from photographers or satellite data all over the world to better generalize the model. You can also experiment with color image denoising, because what we did here was really only concentrated on gray level image denoising. Then what are the applications of this project? Our project is pretty small, but it can still be applied for real world denoising applications, or for as a pre-processing step for multimodal learning. For example, the kind of models that deal with both image and text. Also, we can deploy it as a cloud-based or ML, edge ML based solution.